In November 1967, an experimental aircraft pushed through the sky faster than any rotorcraft before it, a record that would stand for decades. It proved a radical engineering theory correct in every measurable way. And yet, that success would help set in motion a chain of events that ended with a billion-dollar program scrapped, a company's reputation damaged, and Lockheed walking away from helicopter design forever. This is the story of the XH-51A Hummingbird and the rotor system that worked too well for its own good. To understand why Lockheed built the Hummingbird, you have to understand the ceiling that every helicopter design ran into by the late 1950s. Conventional helicopters use articulated rotors. The blades are hinged, free to flap up and down independently as they spin. This design is forgiving, stable at low speeds, and mechanically simpler to control. But it has a hard limit. As a helicopter moves faster, the advancing rotor blade, the one moving in the same direction as the aircraft, generates dramatically more lift than the retreating blade on the opposite side. Push too far past roughly 150 knots and that imbalance becomes unmanageable. The retreating blade stalls. The aircraft becomes unstable, sometimes violently so. Through the 1950s, this physics problem capped helicopter speeds at a fraction of what fixed-wing aircraft could achieve. For the U.S. Army, that ceiling was becoming a tactical problem. Faster troop transport, faster medevac, faster reconnaissance. All of it ran into the same wall. Lockheed believed the answer wasn't a hinge, it was rigidity. The company had been quietly developing this idea since 1949, with an experimental aircraft called the CL-475, testing whether a rotor system that didn't rely on flapping hinges could control the same aerodynamic forces through engineering rather than mechanical flexibility and survive contact with high-speed flight. By 1962, the theory was ready for a real test. In February 1962, Lockheed's Model 186 won a joint Army-Navy program. The mission was direct: evaluate whether a rigid rotor system could survive high-speed flight where conventional rotors failed. The Army designated it the XH-51A. It first flew on November 2, 1962, a compact single-engine helicopter powered by a Pratt & Whitney Canada PT6B9 turboshaft, producing 550 shaft horsepower. Nothing about the airframe was meant to go into production. This was a flying laboratory, built to answer one question. The first version carried a three-bladed rigid rotor, and initially, the theory ran into trouble. At high speed, that three-bladed configuration showed dangerous instability, the exact kind of unpredictable behavior engineers needed to rule out before anyone trusted rigid rotors near a battlefield. Lockheed's solution wasn't a redesign of the whole concept. It was a fourth blade. Switching to a four-bladed rigid rotor changed the aerodynamic balance enough to eliminate the instability. The core idea survived. The execution simply needed refinement, and that refinement worked. With the stability problem solved, Lockheed pushed the concept further. In 1964, engineers took a second XH-51A airframe and transformed it into something closer to a hybrid aircraft than a pure helicopter. They added stub wings spanning 4.9 meters. They mounted a Pratt & Whitney J60-2 turbojet engine, rated at 2,900 pounds of thrust, onto the left wing. This was the XH-51A compound, a helicopter that could unload lift onto fixed wings and add raw jet thrust for forward speed, while the rigid rotor handled vertical flight and control authority. It flew for the first time in April 1965. For 2 years, the compound and its sibling aircraft kept testing the limits of what a rigid rotor could survive. Then, on November 29, 1967, the XH-51A compound reached 302.6 miles per hour, 263 knots, in a shallow descent. To put that number in context, the average helicopter of that era cruised at 80 to 90 knots. The compound had nearly tripled that figure. It was an unofficial speed record for rotary wing aircraft, and it didn't just edge past the competition. It stood for decades a number conventional rotor designs simply could not approach. This was the moment the entire program had been built toward. Not a production order, not a battlefield deployment. Just proof, hard measurable proof, that a rigid rotor, properly engineered, could survive speeds that would tear a conventional rotor apart. By every technical metric the Army and Navy had set out to evaluate, the XH-51A program was a complete success. The theory worked. So Lockheed took the technology that had just proven itself in the air and built something with it. The U.S. Army had a program underway called the Advanced Aerial Fire Support System, AAFSS, meant to produce a new kind of attack helicopter, one fast enough to escort transport helicopters into hot zones and outrun ground fire. Lockheed's answer was the AH-56 Cheyenne. Built directly on the rigid rotor technology the XH-51A had validated. On paper, it should have worked. The underlying physics had already been tested. The speed was real. The stability problem had already been solved years earlier, on a different airframe, under far less pressure. But a successful experimental program and a successful production program are not the same thing. The Cheyenne ran into serious technical problems of its own, separate from the core rotor system, but severe enough to cause repeated delays. Those delays collided with something the engineering team couldn't fix: rivalry between military services over what the aircraft should be, and the political fallout that followed. The combination proved fatal. In 1972, the AH-56 Cheyenne program was canceled outright. It was Lockheed's last helicopter, not because the rigid rotor failed. The Hummingbird had already proven, in the air with a record-setting flight, that the concept worked exactly as intended. The Cheyenne failed for reasons that had nothing to do with the technology that gave it its speed. There's a particular kind of irony in engineering history when the experiment succeeds and the application built on top of it doesn't. The XH-51A did exactly what it was designed to do. It proved a rigid rotor could handle high-speed flight when conventional rotors couldn't. It set a speed record that stood for decades, a number that says everything about how far ahead of its time the concept was. But proving a technology works in a laboratory aircraft is not the same as fielding it successfully in a combat program shaped by budgets, service rivalries, and politics. No engineer can solve with a fourth rotor blade. Today, both original XH-51A airframes are preserved at the U.S. Army Aviation Museum at Fort Rucker, quiet artifacts of a program that achieved everything it set out to prove, attached to a legacy that, for Lockheed, ended in cancellation. The rigid rotor concept didn't disappear. It influenced rotor designs for years afterward. The Hummingbird's success was real. It just wasn't enough to save what came next. If you want more stories where engineering triumphs and program failures collide, subscribe. There are more of these histories to tell.